Hi, I'm Rich with INSIDEHPC. We're here at ISC'14 in Leipzig, Germany, and we're here at the DEEP project booth, and we're going to learn more about what this project is all about and actually see some of the prototype hardware. So let's start with you. What is DEEP all about?
Yeah, well, the DEEP project is one of the Exascale European projects in which what we are doing is we are proposing a new architecture for HPC. This is a new heterogeneous architecture where instead of having the accelerators just as a device of your host, we are using them in an autonomous way. We are building a cluster of accelerators that we call the booster. We connect it with an HPC cluster, and then you can profit from both the good things from the Xeon and from the Xeon 5 processors.
Wow, that's very intriguing, but what about the software? I mean, that sounds hard.
Yeah.
Is that where you come in?
Yeah. So, obviously, the platform is quite different from what users are used to right now. So, which means that basically they really have to tear their applications apart and put them together in a different way. But of course, we have to help them by doing that. And within the DEEP project, we also develop a quite significant software stack that shall help the users to really port their applications. So on the one hand side, this is based still on MPI, so we assume that the applications the user starts with are based on MPI. So and for that we extend the MPI in a way that we'll have an MPI on the cluster side and an MPI on the booster side. And then connect it together with MPI. So basically, or actually, MPI already has all the ingredients that we need there. So there is a call MPI spawn, which was introduced in MPI 1, so 15 years ago. And finally we found an application for that. And so we can really use this call in order to offload parts of the application from the cluster side to the booster side.
Okay, so using this MPI in a new way, but with kind of an old technique, sounds like a real challenge. I mean, this hardware doesn't exist yet. How do you go about that?
So it exists partly. So we have some early prototypes, and we set up some, we call it evaluators, where we try out the new technology, and then we put these evaluators together in a way that we can do a kind of mock-up of the final hardware, and we use this as our development platform.
Okay, so we've got prototype hardware here. What are we looking at?
So we are looking here at the new DEEP hardware that we have developed in this project. We are the integrator of all the functionality that Norbert just has explained. So we try to enable all this functionality in 3 different boards. That's a bridge between the InfiniBand domain and the Exascale domain, a backplane that distributes all the signals in the system, and then the computing nodes, which holds 2 Keynes heat cards, and everything is liquid cooled. So we are not only trying to implement this in a way that it functions, but also that it functions in an energy efficient way, and that it offers opportunities to measure all the data that they want to collect from this machine in a high frequency data collection network. And that all is integrated in a way that we can fit 512 of these cards into one rack. And to make such a dense design, we have implemented and reused our Eurotech Aurora technology for the liquid cooling and also the backplane, etc. So here you see one element, and we will place 32 of these elements into one rack. So this is actually half a backplane, and we will put 16 of these chassis, so 2 halves into one rack. The big difficulty that we have is that we need to cable all these to form a torus, and for that you need a lot of space. So that's why you see a high number of connectors. But if you look at one of these connectors, it's more than 1 terabit per second per blade that goes over this backplane to its neighbors. That's a very huge speed that is only possible with Exascale. But the Exascale guy will explain that to you later.
Okay. And what's the processing element? Is it an FPGA for this purpose?
Yeah. So we started to build this prototype based on the FPGA. The ASIC is coming, but we had to decouple these 2 paths because we can't make 2 of these hardware elements depending on each other. So that would be too risky for the project. So we implemented the FPGA, and we got the partnership with Heidelberg University to program this FPGA, and we are doing the bring up together. So that's the FPGA is not only used to implement the final architecture, but also to debug the board.
All right, so you know, I'm a little confused here. What's the difference between the Deep project and the Deeper project?
Yeah, so in Deep we presented the concept and this new architecture. In Deeper we are going a step farther and we are adding into this architecture I/O, so additional new memory technologies, and going also to support I/O intensive applications and resiliency. And one of these memory technologies we are looking at is the network attached memory that you see here, a device of it.
Okay.
And now it's my colleague this is done by the University of Heidelberg. He can explain you the details of this hardware piece here.
Well, thanks for showing us this. So this is an I/O device, is it? Is that the idea?
So this is actually what we refer to as a network attached memory.
Okay.
So right here in the middle you have a hybrid memory cube.
Yeah.
And as you can see, it's like it has 4 links. You know, a hybrid memory cube has 4 links,
yes.
4 independent links. And you can access each of these links using different types of cables.
Okay.
So here, for example, you have a FMC connector, which is pretty often used on Xilinx devices and evaluation boards. Here you have HDI 6, like 2 times. And you can also access the HMC using the PCI Express edge card connector. So, that's the one thing I would like to show.
Yes. Okay.
And what's the very interesting thing is, what we have here, it is the Xilinx evaluation board for Vertex 7.
Okay.
And it has implemented a hybrid memory cube controller IP. So, with this IP you can connect, you can plug this board onto the to the HMC, like using this FMC connector.
Yeah.
And running with like 1 link, 8 lanes, and 10 gigabits per lane at the moment. We're going to extend this in the future, but so that's the current.
So this was a commodity device that you're able to use for your prototype to see how it would all work together?
We're just using it for prototype. And,
yeah. And how long have you had the hybrid memory cube to work with? I mean, this is a pretty new device, is it not?
It is. It is. So it took us like over a year of work, and yeah, I know it is new. You know, you have to find out
exciting.
Stuff.
Yeah.
It is. Definitely.
Okay. Well, great job.
And just one last thing. What's so pretty exciting about a hybrid memory cube is we would like to, just plug some memory into the network.
Oh, I see. Just like another discrete device that might plug in, like a NIC or something?
Yeah. And the pretty cool thing is, you can just attach like additional memory just to it, just using additional links. So you can connect the evaluation board to the HMC prototype board.
Yeah.
And then you can just use this link and just attach another HMC prototype,
So network attached memory.
Exactly.
And that sounds very NUMA-like to me. It might have different access times and everything like that. So that's intriguing. Very cool.
Yeah.
Wow.
So this is a set of scientific applications we are using to actually validate our deep architecture. Well, they come from several fields of science, actually with a connection to everyday life. It starts with life sciences, simulating the brain activity, eventually the full human brain, well, maybe in 10 years. Okay. We have theoretical physics, this time high temperature superconductivity. So you want to know which substances are really promising if you want to have room temperature or close to room temperature superconductivity. We have a very complex computational fluid dynamics code here. And this is being used in aircraft and helicopter engines. Really optimize those. This is an astrophysics code that predicts solar storms that hit the Earth. There's a climate code that couples climate simulation with actually simulating the atmospheric chemistry, so you can track what pollutants actually do to the weather and to the atmosphere. And finally, we have an industrial code for seismic imaging, which all companies use to actually find out how the various strata in the Earth are oriented, so that they can find places where they could find, well, where you would expect oil or gas. So these are these 6 that we use for the Deep project. All of them have been ported to use the Deep programming model, and well, once we have the
test system build up towards the autumn, where we will really get performance results here. And in the meantime, a sister project has started called DeepER, which uses a little bit more advanced technology than Deep. Well, there are 5 additional applications. Again, one from life sciences. This time we're actually simulating what happens to human tissue if it is exposed to electromagnetic fields or radiation. We have another seismic imaging code, again used by oil companies, this time a different algorithm, a little bit more novel algorithm. We do have an earthquake simulation. Well, this is trying to find out how the Earth is structured.
Yes.
And this is simulating what happens if, well, you get an earthquake, which of course is very relevant and interesting. And this one has, well, actually today won the prize for achieving more than a sustained petaflops, which is really, really a cool
That's
result
exciting.
from LSZ.
Yeah, yeah.
Then there's astrophysics, in this case, a code that would actually process radio astronomy data from many thousands of little telescopes. And finally, there's QCD, quantum chromodynamics, and well, these guys are still trying to find out what holds everything together.
Yeah. So a very broad range of real science that people are trying to solve today, and applying that to a new potential architecture that could change how they do their work, maybe.
So the work there, yeah. The way we structure the work is that we have the experts in the applications, and we have a support team, again, from some of the centers that work there that help them to find out how to change the applications, how to improve performance, how to avoid mistakes. So it's kind of a joint action between computer scientists and the domain specialists here.
Okay. And then how do you model this? Do you have it hooked up to a big array of Xeon Phis and Xeons and seeing how it maps? Or?
Well, we use existing Xeon clusters as one of the porting targets, and we use some Xeon Phis also to find out how the performance there is. And then you can, well, predict where you stand. And once we have the system fully working, well, we will verify it. Also, we have some interesting performance prediction technology here by Barcelona Supercomputer Center that we're also using.